Assalamualaikum and a very good day to everyone. So today we're gonna learn on our final chapter, which is quantitative structure activity relationship. It's the topic relates to chem informatics, whereby it can combine the knowledge on chemometrics and also knowledge on computational and also data, which means like activity lah. Okay, so let's check out the lecture. So I will start my class today uh, by giving you an article on computer, brain and earth battle insect repellent. So apa yang awak tengok kat sini ialah basically ada dua tangan. Salah satu tangan diletakkan insect repellent dan satu lagi tak letak lah. And then dikenakan mosquito. Maksudnya masukkan mosquito dalam box tu dan kita tengok mosquito tu tak pergi kepada tangan yang kena insect repellents. Yang satu lagi dia pergi. Banyak ni. And then so macam mana dia dapat the formulation of DID ni, dia panggil this mosquito repellent as DID lah. Macam mana dia dapat? Dia menggunakan machine learning to get the best structure ataupun the best possible insect repellent structure, and then baru dia synthesis lah. So what happened is from the set of possible insect repellent, dia train dengan komputer to predict the structure of possible repellent molecules and found several that are much more effective than the current gold standard repellent. So based on the gold standard repellent punya structure, dia create a new structure yang could give possible candidates as an insect repellent. Okay, so basically researcher went through the database of insect repellent over yang insect repellent punya database tu dah lama 60 tahun, that contain more than 40,000 chemical structures. So that's a huge one. So nampak, this is how chem informatics is applied from data from a database. Data daripada database dia ambil, dia collect, and then they get the structure and activities, and they select a class of compound called N-acyl piperidines to further investigation as a candidate of insect repellent. So main basic dia ialah group yang ada N-acyl piperidines. These are to identify novel structures with potential repellent activity. So dapatlah finally dia dapat from a trained data, from the 40,000 data and with activities, they get possible new structure of a possible repellent yang exceed the gold standard repellent. Maksudnya dia lagi baik daripada gold standard repellent, yang terbaik itu dia lagi baik. So nampak tak dekat sini bahawa komputer with machine learning and knowledge from previous data, kita boleh form something yang form new drugs atau form new inhibitor, form something yang boleh solve chemical problem lah. Ikutlah saya guna artikel ni sebab dia lebih kepada Malaysia, di mana kita banyak sangat nyamuk kan. Kalau benda ni boleh dapat dekat Malaysia, so baguslah, boleh mengelakkan daripada sakit dengue. But anyway, yeah, this is how important machine learning and also computer in predicting new structure. in our life, we will come across a few compounds or a lot of compounds that have similar activity ataupun similar behavior. Okay, for example, drug yang ada jenis-jenis drug tu memang kita tahu dah kalau ada structure ni, mestilah dia dalam bentuk drug yang sekian-sekian. Ataupun drug untuk macam heroin, morfin, kodin, semua adik-beradik kan. So, dia mempunyai sifat drug untuk tahan sakit dan sebagainya. So, we can actually correlate this structure and also the activity ataupun the behavior of that compound. With this understanding, QSAR is kita pun buatlah QSAR. QSAR is what? Ialah quantitative structure activity relationship. That's another one. We call it as quantitative properties activity relationship, or we call it as QSPR. Dua-dua ni lebih kurang sama, cuma satu guna structure, satu guna properties, physical properties lah, psychochemical properties lah, something yang kita measure dalam bentuk dalam sifat-sifat kimia dia. Okay, so what does QSAR means? That QSAR does, it correlates the measurable or calculable physical or molecular properties to some specific biological activity in the form of an equation. Biological activity can be in the form of QSAR, tapi QSPR lebih kepada psychochemical properties like inhibition and so on. Itu bukan biological kan? Biological ni berrelates dengan biology. Tapi kalau other than that, we call it as QSPR. Alright, kita tengok equation dalam QSAR ataupun QSPR. First, kena ada biological activity, which is the response ataupun activity lah. Biasanya activity ni kita dapat daripada experimental work. And then on the right side is the structural properties. Dan juga regression coefficient K tu. So D1, D2, D3, D4 is the structure. Sifat structure nombor 1, sifat structure nombor 2 dan seterusnya lah sifat-sifat dia. Also known in QSAR, QSPR as descriptor. Kalau dalam chemometrics, we call it as variables ataupun features. Okay, so sama benda tu. Cuma bila dia dalam bentuk QSAR, kita panggil dia descriptors. Alright. Once a valid QSAR has been determined, it should be possible to predict the biological activity of related drug candidates before they are put through expensive and time-consuming biological testing. So, kenapa orang buat QSAR? Is because based on the data, the existing data, sebab mesti orang dah buat a few activities on a certain list of compound kan? Compound, and then based on that compound, we can do a correlation. Ni relates to about or relates on calibration, also regression. And then we can do prediction. From there we can do prediction if we have a new compound yang lebih, ataupun we want to suggest a new compound that have similar structure or similar properties. Can this also predict activity of the biological activity? So with this equation and with this understanding, we can model a very good equation, and also we can predict. From there we can predict an unknown for its activity lah, supaya bila kita dah dapat predict, we don't have to synthesize a lot of compounds. Rather than doing that, what we do is we just predict a few. We just choose a few yang the best prediction, and then we do the experimental part. So that's why it is a timely advantage lah for this type of activity ataupun this equation solve a lot of cost and time punya kepada chemist or any biologist lah. So konsep QSAR atau QSPR ni actually like this, macam ni lah. Kita ada QSAR, QSPR, dua-dua sama, but basically based on that we find out the molecular descriptors of physical chemical properties, and from that physical structure properties and also physical chemical properties, we do some statistical analysis ataupun chemometrics lah secara ringkasnya. So from that statistical analysis, dapatlah sama ada QSAR atau QSPR. Fungsi QSAR dan QSPR ni ialah, first, kalau QSAR ni lebih kepada virtual screening, nak tengok target receptor of a certain drug, boleh tak dia buat, and also we can also model new structure ataupun predict new. Kalau daripada structure yang ada, kita boleh screen to get the best drug, or we can also predict new molecular structure or new molecular modeling lah. We can create new structure, new compounds. And then for QSPR pun lebih kurang sama juga, based on the ciri-ciri molecular descriptors and physicochemical properties. What happen is we can it use a lot in the plasma protein, transporters, metabolic enzymes, and also permeability absorption. Okay, dalam ciri-ciri to determine this kind of properties, transportation. Ni physical, banyak physical properties lah. But basically you use cheminformatics, computational chemistry, and also chemometrics to solve this problem. So these are the problem or tasks. Okay. So this diagram shows the QSAR and QSPR approach. So first they start with molecular structures, either relates with activity, biological activity ataupun property kan, inhibition ke, physicochemical properties, and then start dengan structure and end with properties ataupun activities. So sebelum kita dapatkan the relationship, we have to have the data dululah. So structure kita boleh generate the data, and properties we can get the whole experimental data lah, ataupun we do ourselves the data of the properties and activities. And from the molecular structure, we represent the molecular structure with structure descriptors. Maksudnya daripada structure tu kita boleh dapatkan certain descriptor lah. Descriptor ni apa? Descriptor is the variable dalam chemometrics. So variable ni adalah sifat-sifat, ciri-ciri, tak kisahlah concentration ke, ataupun reading from IR ke, reading from certain instrument, can also come from experimental work. For example, dia punya size, molecule structure. Okay, so from that molecular structure, we can generate 2D and also 3D representation, and mesti ada banyak, and sometimes dia sampai 2000 descriptor. So if it's too much descriptor, it's good, but we have to select the best descriptor. So that's why they akan go through a feature selection and modeling to model the best persamaan or function or equation, and then barulah kita compare dengan properties, sama ada can it really predict that properties, and compare with the previous properties yang kita dah generate. So kalau it's a good one, means that it's about 70 to 100% punya prediction lah. Okay, so dia akan do the prediction in after the model, after you create the model. So this is another way of explaining what I tried to explain just now, whereby you start with a molecular structure and do the structure representation. So from here you get the molecular descriptors and response variable. Okay, so kalau ingat lagi matrix yang macam ni represent the multivariate analysis ataupun PLS, PCA, you can get this type of descriptor lah. And then from there you do regression ataupun calibration to get the statistical analysis. So information of the molecular descriptor and the response is the activity lah, and then you do statistical analysis. Statistical analysis ni sama lah macam chemometric sebiji, but basically because it's based on the structure, we call it as QSPR ataupun QSAR. And then lepas kita dapat statistical analysis or equation or model, we validate with the real activity. Okay, so when we do the comparison, if we get similar comparison, ataupun percentage similarity dia sama dengan QSAR kita, so we have a very good model lah, and we can predict other type of structure. The QSAR is actually first applied by Hans in 1969, where he developed equation that relates biological activity to two descriptors, which is electronic characteristic and hydrophobicity. Masa dulu-dulu electronic characteristic and hydrophobicity hanya orang guna dapatkan melalui experimental, but with the towards time dia perasan yang electronic characteristic ni boleh juga diperolehi dengan calculation of certain group. So setiap satu group tu ada dia punya value, and then dia boleh jumlahkan, then you get the octanol over water partition coefficient, Hammett substitution constant. Dua ni lah, octanol over water partition and Hammett substitution constant. Ni constant K constant ni is just from regression analysis lah. And then C is the minimum effective dose. So dia punya activity ialah the effective dose. Based on electronic characteristic and hydrophobicity, dia nak dapatkan minimum effective dose. So this concept can be predicted and applied to other type of structure that or drugs that they want to determine ataupun predict the minimum effective dose for that certain drug. Log P is a measure of drug hydrophobicity, which was selected as a measure of its ability to pass through cell membrane. So kenapa dia pilih log P? Because dia ada sifat drug hydrophobicity. Sebab drug ni ada bahagian hydrophobicity, ada bahagian hydrophilic kan. So that's why dia adalah log P octanol over W, that reflects the relative solubility of the drug in octanol. Octanol ni represent the lipid bilayer of a cell membrane, and water tu pula represent the fluid within the cell and in blood dalam badan kita. So that's why log P is chosen. Before this, log P is measured experimentally, but after a while they can calculate the log P value. To calculate log P actually can be represented by group additivity approach. Ni saya kata tadi, each of the group ada nilai tertentu. Okay, awak tak payah hafal lah apa nilainya. Kalau saya akan bagi dalam bentuk table lah kalau perlu explain ataupun predict. But basically predict the log P. But basically kalau daripada table dia lah, if you have a structure like for example benzene CH2Br ni, what you can do is just calculate each of the parts in the group compound. So dia ada aromatic ring 1 jadi 0.7. So dia ada 7 H on carbon. Setiap satu carbon ni ada hydrogen kan. So ada 7 hydrogen, 1 2 3 4 5 6 7 kan. 7, so nilai dia lah 1.589. Ada satu carbon yang berhubung dengan bromin, ada nilai ini. Dan satu alkyl carbon CH2, nilai dia ini. So when we sum it up together, we got the calculated P as shown here. So kalau ada lebih complicated structure, means that you have to have more complicated algorithm lah, including factors such as the dipole moment, molecular size, and also shape. So bukan hanya bergantung pada log P, but also you can also add more descriptors, for example, dipole moment, molecular size, and also shape. Okay, Hammett is substituent constant pula dalam Hans approach tadi, Hans punya QSAR tadi. Hammett substituent constant reflects the drug molecule's intrinsic reactivity, which relate to electronic factors caused by aryl substituent. Ni substituent lah, function of the substituent in the drug. In a chemical reaction, aromatic ring substituent can alter the rate of reaction by up to 6 orders of magnitude. So, dia dapati the aromatic ring ni boleh menentukan, adalah salah satu contribution to the dosage of drug lah. What is Hammett substituent constant does is dia check in Hammett substituent constant, it's a constant sama juga macam tadi. Dia akan take certain value ataupun aromatic ring substituent, and then dia akan calculate each of the substituent to certain value. Okay, so for example dekat sini the 10 to the power of 5, the rate of reaction of this structure is 10 to the power of 5 slower bila dia ditukar dengan NO2 and when it's changed to CH3. Okay, so kalau di CH3 dia akan lebih laju, the rate of reaction dia akan lebih laju. So depends lah. Bukan yang bahagian ni, yang bahagian ni X ni. So X ni kalau kita letak NO2, tindak balasnya akan slow. Tapi kalau kita letak CH3, tindak balasnya akan lebih laju. So that's why Hammett substituent constant ni is important and included as the descriptors in the Hans approach. So just now we know that the substituent plays an important role in determining the rate of reaction. So Hammett observed a linear free energy relationship between the log of the relative rate constant for ester hydrolysis and the log of the relative acid ionization constant for a series of substituted benzoic ester and acid. So dia nampak pula relationship between the hydrolysis ester hydrolysis dengan the acid ionization of the benzoic ester and acid. So dia dapatlah from this log you get rho and sigma. So rho ada banyak nilai kan. So if they assign rho with 1, the reaction constant of 1, dia akan dapat constant sigma. So from that Hammett equation, you got the constant sigma over here highlighted in red, and then with that, ni basic lah. Maksudnya kalau just kosong COO ester punya hydrolysis ni kan, you got different substituent, with different substituent you got rho, and then sigma, bukan rho, dapat sigma, and then rho sama dengan 1 lah. So this concept can be applied different list of reaction lah. Okay, first kita dapatkan substitution constant, and then we also got the reaction constant rho. So from this value we can calculate a certain reaction. So to recap, from Hammett equation, we got substituent constant and also reaction constant. Substituent constant ialah sigma and reaction constant ialah rho. So and then the rho can be form in the table lah. Dia ada list of sigma and also rho, and it's a standard lah, constant. So you can calculate for any value. If you can calculate for reaction value and also substituent value. Okay, and the substituent value pula, if you have electronic effect, if you have it, the substituent value pula, it shows the electronic effect of the substituent, whereby the electronegative value, no, electronegative pula, the negative value contributes from the electron donating, and the positive value contributes by the electron accepting group. So yang ambil dekat QSAR ialah ni lah. But all these things daripada Hammett, cerita pasal Hammett ni ialah macam mana Hammett derive from experimental work into a calculated punya information. Okay, on substituent and also on the reaction itself. Okay, tadi kita lihat tentang substituent constant, reaction constant, from Hammett equation, that show us that the experimental work can also be calculated using all this formulation lah, equation and everything. And that is that's why it says dia katakan that kind of thing are the molecular descriptors that can be calculated or measured. Other type of molecular properties that you can have in QSAR is like density, ionization energy, H vaporization, molecular weight, hydration, H hydration, lipophilicity parameter, pKa, boiling point, refractive index, dipole moment, reduction potential, and others lah. So these are measurable properties in QSAR. Maksudnya kita kena measure dalam bentuk measure dalam bentuk eksperimen lah. Okay. Another molecular properties in QSAR can be calculated sama macam Hammett tadi. These are the calculated ones like Ovaltine, Homo energy. Homo ni tahu kan? Homo lumo ni kan? Tahu kan? The highest orbital molecular highest occupied molecular orbital energy dan lowest unoccupied molecular orbital energy. So for orbital itself menentukan how reactive a certain molecular can be. Maksudnya dia menentukan ciri-ciri molekul tu sendirilah. So this list are the calculated ones. Polarizability ni pun calculated, boleh calculate lah. Macam Hammett constant dengan macam Hammett constant tadi, from the substituent constant and also reaction constant. And then van der Waals surface area, molar refractivity, hydrogen energy, tough steric hardness, maximum positive and negative charge, solvent accessible surface area, charge on individual atoms, and surface area ni homologo dah tahu kan. Charge on individual atoms maksudnya kalau setiap, kan kita tahu kan setiap atom tu dia ada charge dia sendiri, so kita boleh calculate. So these are based on the calculated properties. Some of it are calculated from electronic calculation. Electronic calculation, ingat tak yang kita buat computational study tu, kan kita boleh calculate homolumo. Ingat tak homolumo kita yang kita buat dalam apps, computer apps, handphone tu. So these are properties lah. Kalau kita dapatkan energy tu, kita masukkan dalam sebagai descriptor dalam QSAR. Sebelum kita modelkan nanti possibility, nanti baru kita pilih yang mana yang terbaik that contribute to the a certain reaction or certain activity that we want to check about. So kita dah tahu there are two type of molecular descriptors, molecular properties, which are the calculated and measurable. Measurable tu yang eksperimen, calculated tu yang dikalkulate lah, yang kita boleh secara electronically, electron calculation ataupun secara certain equation yang dah di-form sebelum ni kan. And then kita, after we have recognized the descriptor ataupun the molecular property yang kita nak masuk dalam QSAR ni, so kita bolehlah terus buat the model. So how to do a QSAR is first you have to have your structure. Sebab dia QS kan, QSPR, uh, QSPR dengan QSAR kan. So depan dia ialah structure properties. So structure entry and molecular modeling, you have to have your structure, and then you have to have your descriptor generation. So that descriptor generation tu yang molecular properties yang kita bincang panjang lebar tadi tu lah. The calculated ones, the measurable ones. Okay, and then we do feature selection. What does feature selection means? Maksudnya daripada generator, daripada descriptor tu, we can generate like thousands, maybe 1000, 2000. So from that 1000, 2000 mesti ada certain saja yang kita nak pilih supaya fit with our activity ataupun our property yang kita nak tengok. And then we do QSAR model development. Okay, what does QSAR model development does is you have to have a training set. Maksudnya awak dah sedia ada satu set of data yang yang ada property yang descriptor dan juga property activity ataupun properties lah. Bahagian activity tu ada, bahagian molecular descriptor pun ada. Kalau tadi kita tengok salah satu daripada slide, dia ada X dengan Y. Yang tadi tu, yang tu. Okay, so when you have that, you do the training as usual, training set. Dia lebih kepada principal, bukan, dia lebih kepada supervised type of model lah. Okay, so a supervised type of pattern recognition. So dah ada kelas lah, dah ada kelas, dan awak dah tahu aktiviti, dan awak boleh buat model ataupun equation. And then that is using training set lah, a certain training set. Then after you apply your model, after you've done your model based on the training set, then you model your you validate your model. So how to validate your model is to get an unknown n lah, ataupun a few unknowns that have the descriptor properties and also the activity properties. Tengok, can we really predict the model based on the unknown? Okay, so kalau prediction tu bagus, it's about 70, actually 70 pun tak bagus, 75 ke 75% to 100% punya ni. And actually, dan 100% pun sebenarnya tak berapa bagus sebab dia jadikan your model terlampau rigid. Kalau awak ada dalam 80 ke 90%, that's good enough. Prediction yang 80 ke 90%, that's good enough because you give some ruang ataupun some some space for like other possibilities lah. Ada memang semua orang nak perfectkan 100%. Kenapa tak 100% doktor? Tak, bukan tak boleh 100%, tapi bila 100% dia terlampau rigid. Jadi robot lah. Ini model awak tu kalau awak ada unknown yang macam ada similarity sikit je pun dah macam dia dah reject. Tu model, bukan tu model, to predict a certain yang ada sikit possibility, dia terus reject. Bukanlah tak boleh, tak sesuai lah. Macam rigid. So kalau kita ada model, percentage model kita tu, validation dia about 80 to 90, that's good enough. Okay, 70 pun, 75 pun ada orang terima jugalah. Okay. So again, how does structure entry and molecular modeling works? Ialah awak just get 2D structure from the library. Library bukan dekat library PZ, kat library online, the database, library database tu, mana-mana saja awak cari 2D structure yang awak rasa ada possibility. For example, awak nak cari something yang ada benzene group to look at a certain activity or inhibition study kan. So you find that kind of activity lah, find that kind of structure lah, 2D structure. If you can get 3D pun bagus. Tapi biasa kita dapat 2D, kita boleh convert kepada 3D. Kita pun dah belajar dalam computational chemistry, modeling hari tu. So, it's easily done. No problem. After you model, you get your descriptors. Descriptor can be from experimental works and also measure calculated works. So what is molecular descriptor? It's a final result of a logic and mathematical procedure which transform chemical information encoded within a symbolic representation of a molecule into a useful number or the result of some standardized experiment. So something yang daripada mathematical procedure and also standardized experiment. So you get your molecules and then you represent your molecules. From the molecular representation, you can get the molecular descriptors. Okay, so means that molecular descriptor bukan hanya dapat daripada molekul yang kita generate tadi. We can add sebab macam-macam akan mempengaruhi sifat satu molekul kan. So we want to add all the possibilities. Okay, molecular descriptor is useful because it can give more insight into the interpretation of the molecular properties and able to take part in the model for the prediction of some interesting properties of other molecules. So yeah, so that's the importance of the molecular descriptor. Okay, descriptor ni ada 4 jenis. Tadi dia ada measurable dengan calculated kan. Okay, so daripada 2 jenis tu ada lagi pecah lagi pada 4 jenis, which is topological, geometrical, electronic and also calculated physical properties. Yang tadi tu 2 jenis tu is molecular property ya, bukan descriptor. Molecular properties. Properties can be measured and also properties can be calculated. So to be a descriptor, these are the type of descriptor that you can possibly choose from that represent the molecular structures. Okay, in a topological descriptor, it's actually as the structure of organic compound can be represented as connection tables and graph. So dalam topologi, struktur-struktur tersebut kita boleh convert jadi connection table and also graph. Connection table kita dah belajar kan, graph pun kita dah belajar. The rule of graph theory can be applied to form topological indices. So kita boleh represent lah this molecule into connection table and also graph. For example, atom counts, ring counts. Atom count ni ialah berapa bilangan atom kan. And then ring counts, berapa number of ring, molecular connectivity indices, substructure counts and molecular weight. Semua ni adalah, tapi saya tak adalah explain detail, but these are the example of topological descriptors. Another one is geometrical descriptors. Geometric descriptors are calculated to encode the 3D aspects of the structure. So these are the 3D parts lah of a structure. It can be in the form of moment of inertia, solvent accessible surface area. Surface area kan melibatkan 3D, then molecular volume, length to breadth ratio, and also shadow areas. Then electronic descriptors. Electronic descriptors are calculated to encode aspects of the structure that are related to the electrons. So electronic studies yang macam quantum calculation semua boleh masuk bahagian electronic descriptors. For example, partial atomic charges, sigma charges, homolume energy, sample movement, banyak lagi lah. Semua yang kita dapat daripada electronic calculation lah. Yang daripada quantum calculation ke, daripada apa tu, molecular mechanic calculation ke, boleh saja. As long as we got the value lah of the electronic punya source. And then lastly is the calculated property descriptors. These are the actually it's measurable from experiment, tapi dia dah based on the sama macam Hammett tadi kan, daripada measurable, daripada experimental work kita boleh plot plot dan dapatkan a certain equation. Sama lah macam log P, refractive index, polarizability, physical properties which are estimated using computer method can also be generated. Okay, so there are 4 again, there are 4 type of descriptors. Okay. And then after we know apa yang kita nak, descriptor yang kita nak, kita pun select lah the best selection, best descriptor. This is called feature selection. After descriptor having calculated, kita kena reduce to a set of descriptor as information rich but as small as possible. So can you see that how chem informatics is applied to this? Maksudnya you have a lot of data, thousands, maybe millions, okay, possibility of millions of data or descriptors to describe a certain structure activity, and then you have to select what is the best one. So objective feature selection ni only uses the independent variables and descriptors to discard are identified by pairwise correlation and test of identical value. So ada statistical analysis juga lah to be applied to get the best descriptor. So ciri-ciri descriptor tu kenalah independent. Maksudnya bukan dia bergantung into with certain descriptor. Kalau dia bergantung, kita just ambil salah satu saja. Sebab dua-dua tu akan bagi efek yang sama lah. And then kalau kita pilih salah satu, dia lagi bagus sebab dia lebih ringkas. Kalau kita buat banyak, nak buat apa kan? Efek dia sama juga. And then subjective feature selection which does use the independent variable value is applied to further reduce the descriptor set. So dia pun okay, this is how descriptor is discarded, and this is how we decide which does use the dependent variable values. Okay. Then from there we develop the QSAR model. QSAR model can be generated using statistical computer methods. Seperti yang kita dah belajar tadi, MLR, PLS, neural networks, other things lah, banyak lagi sebenarnya, to generate a QSAR model. SVM pun ada. SVM tu vector apa dah, saya lupa dah, tapi tak apalah. These are the example of 3 model development method lah. Okay, ataupun statistical method yang kita boleh dapat to generate our model. Okay. Then we do model validation. Validate. Okay, tadi tu when you do model generate model, you still have to remember that you have to have a training set. Maksudnya you have to have a set of data yang confirm classification dia apa, and then baru boleh buat model. Sebab macam itulah kan, MLR tu, PLS, semua kena ada. It's a supervised method. Okay, so then you validate your model using your test set. Tadi kita guna training set, and then guna test set. Test set tu apa? Ialah unknown yang kita tahu the classes, and then we test berapa percentage of prediction. Kenapa kita kena validate? To ensure that the model will be useful. And the validation of the model is accomplished by predicting the activity of compounds in the external prediction set. So kita guna test set tadi lah, external prediction set tu. And the error produced in the predictor should be comparable to those achieved for the training set. So should be comparable. Maksudnya kalau ada error tu mestilah similar to what is the generated using training set tadi. Kalau contohnya lah, prediction dia adalah about 80 to 90% in the training set. Kalau dekat test set tadi, it should be also similar to that. Kalau dia sampai 50, kita tak boleh terima lah. Model tu tadi tak sesuai dengan test set yang kita gunakan. So now we move on to example of QSAR. Kalau kita tengok dalam contoh ni, it is believed that this structure known as 3,4 disubstituted NN dimethyl alpha bromophenethylamines, okay, this structure is believed to have an anti-adrenergic activity. Okay, so bila and then the difference is X dengan Y je lah. So this structure is the main thing yang dia nak kaji, and then look at the substituents, whether the substituent mempengaruhi juga aktiviti tersebut. Based on this structure and the substituent, they look at 3 molecular properties ataupun descriptors lah yang dia ambil. Okay, lepas beribu-ribu descriptor structure, beribu-ribu structure dan beribu-ribu descriptor yang dia ambil, this is the best lah. Lepas feature selection tu kan, this is the best, lipophilicity, Hammett sigma and tough steric parameter yang mempengaruhi aktiviti anti-androgenic tadi. Okay, so from there, ni dah final dah lah. So dia dapat beberapa based on that just now, you have they have estimated the activity of 1/C, and this is the substituent yang dia look at, HH, FH and so on lah, boleh tengok. And then these are the 3 molecular properties yang diambil kira, pi, sigma and also E. Okay, from there, this is the value. So this is the regress ataupun the calibrated value lah, ataupun model value. Okay, jadi lepas dapat equation dia dapat semua ni, and then this is calculated value, and this is calculated value of A, and then this is calculated value of B. Okay, apa maksud calculated value of A and B? Kita tengok dia kat sini ada 7.82, 7.88, 7.45, 7.43. Okay, ni persamaan A, persamaan B. Nanti kita tengok persamaan di sana. Okay, persamaan A, kalau kita tengok, bukan persamaan A. Kalau kita tengok, this is the predicted result of different substituent dalam structure tadi tu. 7.82, 7.88, 7.45, 7.43, 49, 8.17. Okay, nampak macam yang merah ni lebih similar to the observation. Yang observe, ini yang aktiviti yang bukan calculated ni. Ini ialah aktiviti yang dia yang real one, yang kita dapat daripada experimental work. Okay, 830 ni pun ada juga similarity dia, but mostly saya nampak macam B. 875, 89, 92, 94, 96, 35, 29. 35, 29, 35. Okay, macam merah, tapi tak apa, kita tengok persamaan dia, how does it looks like. Okay, so equation A tadi yang warna hijau tu, just use 2 variable. Kita dapat log 1/C ialah sekian, and then n is the number of sample 22, R ialah the regression line dia berapa, R. So R ialah 0.94 for equation A, and equation B yang menggunakan 3 variables, equation dia ialah 0.959. equation pula R dia ialah 0.959. So based on this, you can say that we can decide whether you want to use equation A or equation B. But kalau daripada R, kita nampak yang equation B is more near to 1 lah. Sebab R tu kalau 1 tu maksudnya perfect lah. So about 95% prediction ialah daripada 3 variable. Dan actually sebenarnya kalau lagi banyak variable sebenarnya lagi bagus. Dia akan describe more lah. Macam ingat tak kita buat PCA tu kan, lagi banyak PCA tu lagi banyak lah percentage of the principal component, total principal component. But basically it depends on you, the researcher itself. Sama ada awak nak ambil yang apa tu, either maksudnya kan differentnya sikit je, 0.94 dengan 0.95 kan, 0.01 dia punya, about 0.01 or less than that dia punya difference. So sometimes kalau awak nak ignore saja 0.9495 ni similar. Kalau 0.8 dengan 0.9 tu mungkin banyak beza, tapi 0.9 dan 0.9 ni kalau bagi saya better choose the equation A lah. Sebab dia punya similarity dia bukan, dia punya error dia similar to B. Tapi kelemahan B ialah dia lebih more variable lah, lebih banyak, you have to consider more variable. Okay, that's why I choose A. But depends, actually it depends on the interest of the researcher itself, how it wants to model dia punya, how dia nak buat dia punya model tu, how the prediction wants to be done. So itulah dia example of QSAR and example of the output of the training set compare with the training set and test set. Yang tadi kita compare dengan test set lah, prediction dia. And then here is also the number, the equation yang kita dapat. So nanti dalam QSAR awak akan dapat equation yang macam ni, that have certain variable. So daripada 1000 variable tadi yang awak generate, variable or feature, awak come out with like 2 or kalau ni 3. Okay, so itu saja untuk kelas QSAR. Dalam QSAR ni yang pentingnya ialah you should know what is QSAR, what is the molecular properties, definition of molecular properties, dan juga macam mana the process of doing a QSAR. Daripada molecular structure ada 5 kan tadi, daripada molecular structure sampailah awak dapat model, dan what you have to consider in choosing the best equation. Okay, so sampai sini dulu. I hope all the class has been very beneficial to you and you get something from it. So kalau ada apa-apa soalan boleh jawab, boleh tanya pada saya. Okay, bye. And saya minta maaf banyak-banyak atas segala salah silap selama ni, ataupun mungkin tak sampai lecture saya, tak sampai ke hati ke tak sampai maksudnya. But anyway, itu semua kelemahan diri saya sendiri, dan saya minta maaf banyak-banyak kepada awak dan kepada siapa yang terasa lah dengan saya. Dan terima kasih kerana sudi mendengar all my lectures. I hope that we'll meet again soon, dan sentiasa jaga diri baik-baik. Okay, Assalamualaikum dan bye.